Hi. What we have done, what we are in now in the logic design synthesis, the title may be a bit, one word missing there. In the synthesis procedure, we step by step, we set the steps here, and then example serial adder, modular counters, 0, 2, 4, 7 counter, and the last one, this is the one that in this video we are going to examine, that is sequence detector. So we are going to examine two sequence detectors in this video. Let me come out of here and move this down and put open board up. Uh, open board, open board. Okay. There. Let me create this area first. That was in Turkish, you see, so I'm going to delete it. Okay. Now, we said this is a sequence detector. What it means that sequence detector, there's a box. Let me draw that, a box here. There is a bit stream coming in. That's that this is X. So there are many zeros and ones coming in. So in that sequence, I would like to find detect 0, 1, 0, 1 bits. If there is a bit pieces which includes that 0, 1, 0, 1, I would like to get z equal to 1, right? So this is, so I define the relation between input and output. So in synthesis, I'm going to find out what is inside that box. That means which elements are going to be connected together in order to transfer this, in order to do this detection at the output. So that's what we said here is called word description. Word description. The word description is important. Why is that? Because by examining the, by considering the word description, we are going to draw a state diagram. So if we draw different state diagrams, that means you're going to design different things to do the job. Maybe it's not going to do the job that you are looking for. So how I can separate those? So I am going to give you an example to find out the possible alternatives for this sequence detector. Not all the detectors might have that property, but this word description tells us there are at least three alternatives. You see the first row here, input, is the common for all the three, but the outputs that we're going to draw now underneath is going to be different from each other. That means we are detecting the same 0, 1, 0, 1. There are three alternatives. This one is called overlap one. Why we call it overlap? If you look at this black one here, that is our sequence. So at the output we see that. So and then if you look at the red one here, red one has got 2 bits, but the other 2 bits are the first detected sequence. So if I put this, the first detected last 2 bits, second detected first 2 bits, make the same sequence again, isn't it? That is the same as this. So at the output I've got 1 here. What happened? That overlap happened because the first sequence overlapped with the second red sequence. So I have that one output at the output. For example, this blue, let's say dark blue one, is this one is overlapped with the red one. So I've got another one here. And then there's no overlap, it goes like that, and you can detect this sequence once more, you get the output 1 again. So the second one is the non-overlap one. That means when you detect the sequence that you're looking for, you're going to find out a new sequence including all the bits. So you're going to ignore the first one and continue on the second one. So this is this one. If you don't detect the overlapped one, so you're not going to see 1 in that position here. So the red one is going to be this, the new 4-bit sequence that I am looking for. I get output 1 here. So for this, for example, this is another sequence that I am looking for, and the output is 1. That is not our overlap case. The third one is this. My sequence has got 4 bits. So starting from the first time, I'm going to divide all my bits in 4 groups. So let me do it in, let's say, green here. So I am dividing my input 4-bit packets. So you see different colors, you see that. This is another 4-bit, this is another 4-bit. And I'm going to check this 4-bit, whether 4 bits, whether it is the sequence that I am looking for or not. If it is not, put 0. If it is not, if it is my sequence that I am looking for, then it is 1. So it goes like that. You see 0 here, 0 here, and 0 here. So it is just 1, 1 here. So if you compare these outputs now, they are all different, but they are all detecting the same sequence. So you've got to pay attention if something, word description, has got some alternatives to it. So before you start to design, you've got to consider the alternatives, what they are. And then you're going to ask who wants this circuit, whether they mean which alternative by saying that word description. So once you know that, so you can start your design. So how we are going to start our design, we're going to draw a state diagram. So we've got to make the decision, is this going to be a sequential circuit or a combination circuit? Definitely we could say that this is going to be a sequential circuit, because in order to say that that sequence came in, you've got to remember the previous sequence bits. For example, in order to remember that sequence 0, 1, 0, 1. So one thing more, it says there's an explanation in 0 comes first. That means that's the least significant bit. So the sequence is going to come in this order, 0, 1, 0, 1. So your detecting is like that. What I was saying, so whether it is sequential circuit or not. So you've got to remember to say the output 1, you've got to remember all these bits to say that this is the sequence, isn't it? So that means you've got to keep some of the information in your memory. That's why that's going to be a sequential circuit. I can definitely say that. So okay, then in the state diagram we've got the states. So let's consider the first state. First state could be considered as a beginning state. Let's call it A, and beginning state. Why I said this is a beginning state? Because my sequence first bit is 0. If 1's coming in, that means definitely this cannot be my sequence. So in order to start my sequence, this first 0 must come in. So that means in the beginning state, if I've got 1's coming in, my output is 0, and I stay in my beginning state. when I am going to move on, when the 0 comes. When 0 comes, that means I could detect my sequence. So when 0 comes, you're not in the first state, so you're going to come to a new state. So how I am going to name this state B? The best thing to say is first bit of the sequence, first bit of the sequence has come. That's the first bit, isn't it? So my output is 0, of course. So after the first bit comes, if 1 comes, that means possibly I might get my sequence. But if once more 0 comes, when I am in state B, I must go back again, isn't it? Because this cannot be my sequence. So I'm going to consider that's going to be that's going to be the same as my B state, isn't it? If 0 comes here, this new 0 is going to be the first bit of my sequence. So if you consider from here, that is the first 0, that's the second 0. So when the first 0 comes, I am going to say this could be my first element of my sequence. But after the second 0 comes, forget that. That could be my sequence first bit. So it comes back to itself. When 1 comes, while we are in state B, so that means the first 2 bits could be detected, isn't it? So I'm talking about this when 1 comes. So I put here 1 comes and put next state is C. When I put next state C, I should name this next state C. How I am going to name it is easy. First 2 bits of this sequence has come. I can say that 0, 1 came. Okay. So consider we are in state C now. In state C, when 0 comes, what happens is this. When 0 comes here, so that means that could be your sequence, isn't it? The first bit 0 came, 0, 1 came. So the fourth one is going to be D state. Let me change it to a different color. Let's put it like this. When 0 comes, it's going to be D state. The name of the D state first 3 bits of the sequence has come. 0, 1, 0. Right? Okay. So what happens if 1 comes in state C? We missed that. So 0 comes, you came to it, right? If 1 comes in, let me use it red again. When you are in this state, that means 0, 1 already came. Now 1 comes in. If this 1 comes, what you're going to do? That means you lost your sequence, isn't it? When you lost your sequence, you're going to go back to the beginning to look for the other 0 to come in. So that's going to be this one. If 1 comes, output is 0, of course. So let's examine D now. So this color, I change this color once again. So when 1 comes while you are in D, that means you detect your sequence, isn't it? So the output is going to be 1, definitely, when 1 comes. When 1 comes, we are examining this overlap case. So that means uh, your you detected first sequence, and you also detect the second sequence first 2 bits. That means that's C state, isn't it? So when 1 comes, you're going to come back to that C, and your output is going to be 1. Why I came to that C? Because C says the first 2 bits of the sequence 0, 1 came. So when 1 comes here in that state, so you're going to say that this 0, 1 is going to be the first 2 bits of the next coming sequence, right? So this is just to show you what's happening here. So okay, when 1 comes, you go back to 0. When 0 comes, what happens then? You are in this state D, 0 came in. 0 came in, that means that's going to be the first bit of your sequence, isn't it? So you're going to come to that state B. So when 0 comes, you're going to come to this. And you didn't detect the sequence, so you put 0 here. So these are missing, of course. This green one, I'll put it. We haven't seen the sequence yet, so it's 0. And for this one, the output is also 0. So output becomes 0 in this position only. Now we found our state diagram now. When we found our state diagram, you've got to write the definition of these states. If you don't write this definition of these states, somebody who tries to read your state diagram cannot understand whether this diagram detects this sequence or not, because you didn't define these states. So you must give your states definition. We show them as A, B, C, D. So if we assume that these are the minimal number of states, then we could say that the next step you're going to do is give the assignment to those states. So you could give any assignment to those states. When I said any assignment, do I write or not? So you can prove it easily. So you look at this now. Input-output relations are those relations, isn't it? So whatever code you give for this A, B, C, D, input-output relation does not change. That means your circuit does the job. Input-output relation is not changing whatever code you're going to assign to these states. But what will change is your circuit inside of that box is going to change. Maybe you're going to use higher number of gates or less number of gates, depending on the state assignment. The number of gates that you're going to use is going to change. When I say number of gates, it changes, not the number of memory elements, because number of memory elements related with the number of state, isn't it? Not the state assignment states. So if you got 4 states, you need 2 state variables. That means you need 2 memory elements for this. Let's come to second stage. Let me clear this area. So this diagram, although it doesn't seem the same as the previous one, it is the same actually. If you examine it your own, you could see that this diagram is the same as the previous one. So this is the same thing. So one of them is in line, the other one is in 2 lines. So the definitions are the same, and state coding, so do this coding, so you could choose any coding, because we didn't examine the state assignment methods, so you could give any assignment you like in order to find out a circuit. Now the next thing after you draw the state diagram is put the state table in. Why we are putting the state table in? Because we would like to find out output functions, and we would like to find out the memory element input functions. In order to find out memory elements input functions, we need to next state functions. So that means that's the mathematical model, isn't it? Next state functions and output functions. So this tells you this. So since we've got two state variables, two state variables, what are they? Y1, Y2. These are independent state variables. That is our X, our input. So these are the independent variables. So next state function here and set functions here. How I'm going to find this one from this diagram? I will show you just one of them, so you could do the others your own. So look at this state independent state variables, y1, small y1 and small y2, 0, 0. So that's 0, 0. So 0, 0 is state A, isn't it? So that means that is 0, 0 state. So this is your present state. Present state. My input is 0. Put in different color. My input is this. So my input is this, that means that, isn't it? When the clock pulse comes, so sequential circuit, synchronous sequential circuit, when the clock pulse comes, your next state is going to be B. Next state is going to be, make it different color, put it that one for example. Your next state is B. So what is B is 0, 1. So if you look at this diagram, this is B, isn't it? That is B and that is A. So if your present state A, when input 0 comes, your next state becomes B. 0 state, input 0, your next state B. I wrote that. So what about the output? Output is seen in here, make it different color, make it red. So this is the output, isn't it? Output. And the green one is the input. So that is the output then. That is the output, red one. This is this output. So you're going to repeat all that for all these lines. So that means you're going to find out all these zeros and ones. Once you found this, that means you found next state functions and you find the output function. That is the mathematical model. What you're going to do next, find out the memory elements input functions. If you choose any memory element apart from D, you're going to use inverse definition relations. In here, we have chosen the D-type memory element. I know that the D-type memory element next state function is the same as input function. So these are my input function. Automatically, I found them. So I'm going to design D1 and D2. Find the minimal functions for D1 and D2. You're going to get this and this. So what about Z? Z value is equal to 1 in only one place, here. So by looking at the independent variables, you can directly write it in internet. That is going to be y1, y2 prime, x. So if you look at here, x, y1, y2 prime, that is z. So this is our box now. This is clock, and x prime comes here, x directly comes here, x directly comes here, x prime comes here. So you see, one input, one output. So this is our sequence detector the sequence that we detect is 0, 1, 0, 1 overlap case. The second sequence detector that we are going to examine is 0, 1, 0, 1, 1, 1 detection. That means 3 bits, one after another, if they are all 1. So you're going to give the output 1. 1, 1, 1 detector. So once again, we've got states here. So the previous one was a milli machine, isn't it? So you could see it milli machine because it depends on x here, that x. Okay, so that x output function depends on x and the state variables, then it is a milli machine. This one is going to be a Moore machine. How it's going to be a Moore machine, I'll tell you. So A state is the beginning state, B is first bit of sequence 1 came in, and C first 2 bits came in, C first 3 bits came in. So first bit came in, so when it is 1 you came here. This is second first bit came in, B. So that second bit came in, C. Third one came in, D state. So for the other cases, you cannot detect this one after another ones in a sequence. So for example, if you are in state B, that means first 1 came in and then 0 came in, you're going to go back to beginning because your sequence starts with 1. So you've got to go back. So for this C as well, you're going to go back. For D as well, you're going to go back. So that is the critical point here. When you are in state C, that means 2 1s came in. 1 1 came in, 2 1 came in here. When 2 1 came in, another 1 come in, you're going to come a new state. It says 3 1s came. Let's say the 3 1s came in. One after another, I should have said that one after another 3 1s came in. So these states just tell me where it is going to be 1. Your output is going to be 1. So that means that's why I made it a Moore machine, because in this state A, B, C, your output is 0. When you come to this state, since the state is the one after another ones came in, so in this state your output is going to be 1. That is the 1. So let's say 3 1s came in, another fourth one came in when you are in D, still you're going to get the same output 1, isn't it? Because you are looking for 1s came one after another and 3 of them together. So that means you're going to come back here. How you're going to come to the beginning? Wherever you state in, if 0 comes in, you must go back to your beginning state. So this is a Moore machine, not Milli. The previous one was Moore machine. If you know the state variables, you know the output. So can you write the Z output function in terms of state variables? Yes, you can. But all you need is the D assignment. Let's say D assignment is 1 0, state assignment. So A, B, C, let's say this is 0 0, that's 0 1, and that is 1 1, and this is 1 0. So if you assign that 1 0, your Z output, when you are in state D, your output is going to be 1. That means that is Y1, Y2 prime, isn't it? For that 1, for that 0. So this becomes milli. Z function depends on the state variables only. it doesn't include any input variable in it. So here you are. I don't know whether this assignment is the same assignment given here. So one of the assignment is this one. For this assignment, that's the circuit. So you're going to repeat what we have done in the previous sequence detector afterwards to find out the circuit in order to finish the synthesis operation. So that is the end of this video then. Let me stop.